bell should anyone step over. Our first speaker is Ellie Porath. Please go ahead.
Hello, everyone. Thank you for the invitation. My name is Ellie Porath, and I'll be discussing my work on dynamic polymer rheology. So just a bit of background on myself. I did my bachelor's in physics at U Chicago, and then I did my PhD in material science. Then I did a postdoc at ETH, and now I'm doing another postdoc at ESPCI in collaboration with L'Oreal. And I would say that my research centers around the field of soft materials rheology, with my PhD mainly focusing on these dynamic or self-healing polymers and thin films. Then my work at ETH included doing rheology on bacterial biofilms, kind of treating them like colloidal or polymeric networks. Then I dabbled a little bit in active colloidal particles and how they affect soft hydrogels. Now my work is on the sensation of touch and the quantification of this touch sensation. I can't talk about that because we have a patent pending. So today I'm going to discuss the dynamic polymers instead. So what are dynamic polymers useful for? We can make them into these ultra-thin coatings, which are ideal for these power plants because they increase heat transfer due to water droplet formation. They're also interesting for applications like nanolithography, and their self-healing and hydrophobic properties are great for technical coatings on solar panels or cars or cell phones, personal electronics. Now, what do I mean by dynamic networks? As the video here, you can see that PDMS with permanent bonds versus PDMS with dynamic bonds looks qualitatively similar. But then when I press apply pressure or temperature, the material with the dynamic bonds is able to go back into the shape of the mold that I put it in. So I take this dynamic PDMS and I spin coat it onto a couple different substrates. It's very versatile. And if I even spin coat it onto a roughened aluminum surface, the hydrophobicity of the PDMS combined with the rough surface allows for us to achieve super hydrophobic capabilities as well. Then I want to compare the condensation properties. And so I look at a commercial fluorinated surface, and I want to see stable droplet bubbles, which I do see in the dynamic PDMS for up to 17 days. But in the commercial surface, after only a bit over an hour, we see these bubbles, which means that the water has gotten under the surface and delaminated the coating. We think that this is due to the self-healing abilities of the PDMS. So we tested it and we did a macroscopic cut on the fluorinated surface and on the dynamic PDMS surface. And this is in a humidity chamber. What we're looking for is the condensation of water droplets and their coalescence so that they can slide off of the surface easily. What you see is that the cut pins the droplets on the surface and is therefore not as efficient, whereas the droplets in the PDMS are able to go even over the cut, meaning that the polymer has healed into the cut space. Just as my last slide, I'd like to say that I'm continuing a bit of this work on the side by putting a mold on top of the material before I cure it, and then removing the mold and seeing how the shape changes in the dynamic material, which starts as like a square, and then it becomes a circle over time. And I can take a comparison of the height difference here to see a sort of relaxation time scale of the material. And you can see that as a comparison, the permanent material doesn't change shape over time. And thank you. I will be happy to discuss more.